In this video, we will study how TinyCSP is able to compute solutions for the n-queens problem and for even more other problems as well. The computational paradigm is organized this way. Internally, inside our implementation, we will really decouple the search component from the constraint store. What we mean by the constraint store is that we have all the domains of the variables. For instance, here you have the information that x belongs to the domain 0 to 5. Okay? And acting on this domain store, you've got at the periphery all the constraints. And the constraints cannot communicate with each other. They directly act on the domain store. And you will see that they will be in charge of removing invisible values from the domain store. As the computational paradigm will use a propagation engine that will be able to prune the search space a little bit like what we did before to check that the prefix of the n-queens decisions were still feasible. But instead of doing this very specific algorithm for the n-queens, we will have something that is very generic, and it will manipulate abstract constraints object. And this is the fixed point algorithm. The fixed point algorithm will select one constraint of your problem, check if it's feasible. If it's feasible, it will then apply a pruning algorithm associated with the constraints, and it will do so until no constraint is able to remove any value from the domains. We say that in this situation, we have reached what we call the fixed point, and it means that we might still find solutions inside given the current domain store, and we need to branch further inside the search. If it's not the case, if one constraint detects a failure, then you need to backtrack. You need to backtrack to a previous state and try a different value for one of the variables that you have tried. Okay? So what we mean by pruning algorithm is removing impossible values. I will come back to that later, but let's first see one concrete example. Assume that we have a constraint, C, and this constraint is x less than or equal to y, and the current domains is 0 to 10 and 5 to 6 for the domain of the variable y. Clearly, because x should be less than y, you can already see that you should update this value, this upper value of the domain, up to the value 6. Okay? Because if you would give the value 7 to x, then this constraint cannot be satisfied anymore. So we know that the pruning algorithm of that constraint should update the maximum value of x in its situation to 6. That's for the fixed point algorithm. When is it computed, the fixed point algorithm? It's computed every time the search makes a decision. So every time the search takes one branching decision, like the queen at index 0 should be placed in row number 0, in that case, we compute the fixed point algorithm, and we will shrink the domains of the constraint store using the fixed point algorithm. In case of success, the search needs to take more decisions. For instance, x1 equal to 2, and again, the fixed point algorithm will be executed and so on. If there is a failure, such as in this case, you need to backtrack. Okay, and you communicate to the search, the constraint store will communicate to the search that it needs to backtrack. How is it implemented internally inside the TinyCSP class? Inside the TinyCSP class, we have two lists here, the list of constraints and the list of variables. And the constraints, of course, are acting on the variables. And we will store them inside a linked list. Okay? Let's say that this is the constraint store. We have, of course, a factory method that is able to compute, to create a new variable for our problem. And we have also some methods that will create the constraints. And inside TinyCSP, we have just one type of constraint. We have the not equal constraint with a possible offset. So that's the constraint x different than y plus offset. But you could imagine to add more constraint inside this class if you want to enrich a little bit your solver. We have the fixed point computation. And the fixed point computation is no surprise. It's quite close to the pseudocode that we have seen before. As soon as you did not fix, so as soon as fix is false, you iterate, okay? And you pick all the constraints. So you iterate over all the constraints of your problem and you propagate them. The contracts that you have with the propagate implementation of all the constraints is that if it was able to remove something, then propagate will return false. Okay, so propagate will return false. So if propagate returns false, if it was returned true, it means that it was able to remove something. So if you return true, this will be false, and so fix will be false, and so it means that you need to continue. It means that you didn't reach the fixed point yet. So the constraint is an abstract class, and you have only one method there, that's the propagate method. And the propagate method will return true if any value was removed by the propagation, by the reasoning on the constraint. The variable class has just one instance variable for the domain, and the domain, for now, you can simply think about it as a data structure to represent a set of values. Okay, so that's data structure to represent a set of values. You can imagine many different types of implementation for a set of values. So when you create a variable, I just instantiate the domain. The constraint has two different responsibilities. First, it should check if it's feasible or not, and it should prune, which means remove impossible values if it can. Let's study one concrete constraint, the one that is used for the n-queens problem. X different than y plus a possible integer offset value. So the constructor is only storing the instance variable, okay? And then the propagate method will verify if the domain of X is fixed. If it's fixed to a single value, then you can safely remove from the domain of the other variable, you can remove the domain, the value of X minus the offset, you can remove it from the other variable Y. And if it is the opposite, so if the domain of Y is fixed, then you can remove from X the domain, the value of the domain, the single value of the domain of Y plus the offset. Okay? So it means that you can only propagate something if one of the two variables or the two are fixed. Okay? If this is the case, you return true if this value was effectively removed from the domain of Y. Okay? And in all the other cases, you return false, just to mention to the solver that you were not able to remove any single value from the domain of the variables. The state management now. So far, we have assumed that we were going down in the domain, so we were only removing values from the domains. But when you have a backtrack, you might be in a situation in which you need to restore the domains of a variable. Let's see one example. So the strategy that we'll use is the one of the backup mechanism. So just prior to the branching, we will clone the domain of the variable of X. So if you remember, the variable of X contains a placeholder here for the domain. Okay, so we might easily clone the domain of the variable X. So we will clone as a first step before branching, we'll clone the domain. Okay, and that will be the domain that is cloned. Then we can do the branching. For instance, you pick one variable of your problem and you assign it to some value. Let's say y equal to 2. You compute the fixed point. As a consequence of the fixed point, the domain of X might shrink because some constraint might remove impossible values from the domain of X. And at some point, you probably will need to backtrack because either you want to find other solutions or you didn't find any single solution below, so you need to backtrack and reconsider the decision that you have taken. So when you backtrack, you need to restore the domain. The problem is that the variable X now has a modified domain D prime, okay, the one that was computed below during the fixed point. But before branching, we decided to clone the domain D of X. So what we need to do now is take this clone domain and put it inside the variable X. And so we replace the domain like that. We restore the clone domain inside the variable X. Okay? And so we will have a private method inside TinyCSP that is only in charge of that. It takes a list of all the backups of all the domains of the variables. Okay? And then we will iterate over all the variables of our problem, and we will restore the domain, so instance variable of the domain, we will restore it to the value it has in the backup. Now the DFS. how is the depth first search implemented inside TinyCSP? So the branching that we will do is not the same as the one that we did for the n queen so far. We will do a binary branching. So we will have a branching of this type. We will take a queen and we will say it's equal to some value on the left and it should be different from that value on the right. Okay, that's a binary branching. So we have a method that is asking to pick one variable that is not yet fixed, that is not yet decided. If none of the variable is, if all the variables is fixed, which means that there is no fixed variable, all of them are fixed, then you've got a solution and you accept this solution. So you call your closure to notify the listener that one solution was found. Otherwise, you take the unfixed variable, you take one value inside its domain. Let's say, for instance, that we take the minimum of the domains of that variable. And then we will back up the domain here of all the variables. So we clone all the domains here. So we've got an array list, one entry for each variable with the backup domains. Then we will try this value v for the variable y. We compute the fixed point because of this decision, because we have restricted the domain of the variable y to a single value. You might be able to infer the removal of some other variables during the fixed point computation. And once the fixed point is done, you recursively call depth first search. Okay, that will be the left branch. What might happen here is that you might be in a situation where one constraint detects an inconsistency. Or for instance, you have a domain wipeout, which means that the domain wipeout means that there was a single value left and it was removed by some constraints, which means that one variable of your problem has no possibility anymore. And so there is no solution there. And so an inconsistency exception might be thrown and you might backtrack. Once you backtrack from the left branch, you restore all the domains. Okay, and once you have restored all the domains, you are ready to go to the right branch. That's more or less the equivalent of the left branch, but instead of fixing the variable y to the value v, we will remove the value v from the domain of the variable y, and again we trigger the fixed point and we'll recursively call depth first search there. So you see, it's very generic. We have no assumption at all about what kind of constraints there might be inside our problem. The domain implementation, as I said, so far you could imagine that it's just a representation of a set, a collection of values. And for this specific implementation, we have decided to implement the domain with an internal Java bit set representation, okay? Because that's very efficient in terms of memory, it's quite compact, and it's quite easy to clone as well. So the bit set internally will be initialized to the a bit set of size n. And then we have all the helper methods that you can imagine that are useful for domain. You can check if it is fixed. You can ask the domain what is its current size. You can get the minimum value of the domain, and all these functionalities are just delegated to the bit set internal implementation of Java. For the removal operation, that's more interesting because the removal operation, well, if it's a value outside the current possible range, then you just return false to say that you are not able to remove any single value. But if the removal succeeds, what you might have is a situation in which you just remove the last value that was still in the domain. So assume, for instance, that the domain was a singleton with only 3 inside this domain. If you remove 3, you need to throw an inconsistency exception. And so just after you clear the corresponding bit inside the bit set, if you detect that the size is 0 of the internal bit set representation, you throw an inconsistency exception. And again, if you remember the depth first search, this inconsistency exception is catched there to make sure that you backtrack immediately. If you fix the variable to a single value, you might have the same. Okay? If you want to fix the domain to the value v, and it happens that this value is not even inside the domain, then you throw an inconsistency exception as well. And otherwise, if it's inside this one, you clear all the bit set and you just re-add the corresponding bits. The clone is easy as well. We will just rely on the clone implementation of the bitset object of Java. And that's it. We have studied all the different implementation objects inside TinyCSP.